I would like to be very specific. I will be talking of Feynman's diagrams for a macroscopic system. And this is essentially the beauty of the method, which allows to do something for a microscopic system. So we have actually many collaborators on this project, but the main people are Nikolai Prokofiev, my long-term collaborator at UMass, two postdocs, Chris Van Hoeke and Evgeny Kozik, and Felix Farmer, our former postdoc now. He has just recently got a faculty position at École Normale. And actually this is the complete list of people who are involved in the project, including experimentalists from MIT, from Martin Tverlein group, who recently actually, they're working on resonant fermions, and the idea of our collaborative effort is just to cross-validate. We will validate, actually have validated the experiment, and they validate our Monte Carlo, diagrammatic Monte Carlo results. So what are the principles of diagrammatic Monte Carlo? Well, suppose we have this or that diagrammatic expansion in terms of Feynman diagrams. For example, this one, which can be viewed as an expansion for a polaroid. So we have a particle propagating in a medium. This green line stands for the Baire propagator of particle, and those purple lines represent phonons. So the only thing which we need, the mathematical thing, is the structure of this expansion. So we have some answer. Normally it would be the Green's function. We denote it with U, which depends on some variables. We call them external variables and denote them with the letter Y. Those variables, as you know, can be momenta, coordinates, frequencies, times, real or imaginary. They depend on the representation. So this unknown function is expressed as a diagrammatic series, by which we mean a series of integrals, and the word diagrammatic means that actually each integrand in this series, which is denoted with this letter D, has a relatively simple structure. It's a product of simple functions called propagators. And diagrams basically sort of represented visually this structure and integral. What will be important for us is that all integrations over internal variables, once again these internal variables can be, depending on representation, momenta, coordinates, times, frequencies, all these integrations are understood as a kind of external procedure with respect to the diagram, as opposed to what we do analytically. Analytically, we include integration in the definition of the diagram. So why do I need to emphasize this fact? So basically then, we can view, if we understand this integration as a kind of external procedure, and suppose for a while that all diagrams are positive definite and the series is convergent. So once again, the structure is the following. We have an integrand which is positive definite for a while, for the sake of argument. We have some discrete variable psi, which actually enumerates all the topologies of the diagrams. We have some external variable y, which actually is a set of external variables. And we have internal variables, which we integrate over. And we have such a mathematical structure. Now we can think of the summation and integration as a sort of averaging. So if we interpret this expression, d, which we integrate and sum over, as just a distribution function for these variables, which include internal continuous variables, external continuous or discrete variables, and the variables which, discrete variables which enumerate the topology, we can interpret this expression as if there is some quantity of interest, some function of interest.
What about it?
Yes?
What about internal discrete variables?
Also, this psi is a set of all...
Not just topology, it could be Matsubar frequencies and stuff. Yeah.
Oh, in this case, I would just use it the same way as the integral. So Matsubara frequencies would be over here. So that doesn't matter. So my point is that actually it doesn't matter whether they are discrete or continuous. That's the main point. So we treat everything on an equal footing. That's the idea of just separating the integrand from everything. So summation over all sort of discrete variables, integration over all sort of continuous variables can be understood as averaging over the set of some graphical objects. That's the idea. And this expression is just the probability of having a given probability density with respect to continuous variables of having this particular configuration. And then comes the idea of numerics. Okay, if it's the result of sampling this function of the variables, the function of interest of variables of interest, we can just try, and you will see that it's relatively easy, to generate this distribution of these graphical structures of these diagrams in accordance with this function, so that the probability is proportional to this function, and then we will just sample our quantity of interest out of this distribution. And if this function is not positive, definitely we will be using the absolute value for the simulation, and the sign if it's real, or the phase factor if it's complex, as a kind of observable, which we will be just averaging over this distribution. So that's the idea. Please feel free to interrupt me if something is not clear. Okay, how are we going to sample this distribution? There is a standard way, which is called Metropolis algorithm, and we will be using just generalized, a little bit Metropolis algorithm of doing this stuff. So we start from some arbitrary diagram, very simple. The starting point doesn't matter, and we do some elementary updates, some elementary moves. Normally, with continuous variables, these moves come as a kind of pair of complementary moves. For example, starting with the diagram like that, we can add a propagator, or we can remove a propagator. This is a pair of typical moves which allows us to actually sample all the space.
Sorry, I didn't understand. Do you do the integral in the diagram analytically, or is that part of your sampling?
It's the part of the sampling, and
this
is the crucial.
The integrand also.
Hmm?
The integrand also, not just.
Yes, exactly. So, and this is very important. So, whenever we introduce a new propagator, two ends are supposed to be associated with 2 times. For example, if you work in the chapter, or 2 coordinates, or both. This is how we sample those internal variables. So their sampling comes simultaneously with sampling topologies, not separately. Okay, and let me just remind you basically the idea of Metropolis algorithm, which is known since 1953, and I will explain you the connection, how we use the Metropolis algorithm. So Metropolis algorithm is a generic algorithm to sample some configurations, whatever they are. For simplicity, we can think of discrete configurations of something. So we have objects which are labeled with letters A and B. In our case, those are diagrams. But if we don't want to think of continuous variables at this point, we can discretize all the variables, and we have a kind of set of, infinite set of objects. And we have those letters N, which denote, we want to create an ensemble by this type of elementary updates, essentially Markovian process. We just update step by step, diagram by diagram. We have a Markov chain, and then we have an ensemble of configurations which we have generated. And these ends represent the number of configurations, diagrams in our case, corresponding to a given set of variables A. And we have probabilities of going from configuration A to configuration B. So the idea of the algorithm is to come up with a certain simple structure of those probabilities in such a way that those ends are just proportional to some physics weighting factors. In our case, just diagrammatic expansions, diagrammatic expressions, D, which we are going to integrate, to sample. Of course, there is a continuum of solution to this problem. So what comes from the theory of Markovian processes is that when we do just a decent number of updates, the following equation is always satisfied. Basically, the equation says that the process has saturated to something, to some equilibrium. And we want to come up with such an expression for probability that the equilibrium the Markovian process saturates to is just the one we are looking for, when those ends are just proportional to the physics expressions. And the simplest case and most powerful, most general case is so-called detail balance. So we can observe that if this equation is satisfied, then we are guaranteed that those ends are proportional to those W's, and we are in business. And still, even if we require this detail balance, we still have a continuum of solutions, and the simplest one is the following. So the probability of going from A to B is unity if the weighting factor in B is larger than the weighting factor in A, or it's this ratio, the famous ratio of the two weighting factors. In this case, this probability is just this ratio. And you can check that this detail balance is satisfied, and correspondingly we are in business with sampling. So what delicate feature comes with diagrams is that actually when we do this update by introducing a new element, we have to create new variables. So it's not like we go from one configuration to another. It's like we go from one configuration to a continuum of new configurations. And that's why, in addition to Metropolis, we have yet another name, Hastings. It's basically the idea of sampling everything in two steps. First, you propose something, and then you either accept or reject your proposal. In this case, we have the same ratio of new to old weighting factor, but you can easily notice that this ratio itself now is dimensional. Whenever we have continuous variables and whenever we change them, actually the ratio is dimensional, which clearly tells us that something is lacking. Of course, we can discretize the continuous variables, in which case we will have some differential factors, but then this ratio will be essentially infinitesimally small. But if we add this Hastings element, namely if instead of just going from one elementary differential volume of the phase space to another, we actually propose the whole set of new variables. So whenever we say introduce a new propagator and new variables come with it, we use some arbitrary function W to seed these new variables. And then, as you can easily check, it's very simple. All differential factors cancel each other if we use them. And the bottom line is the following simple formula. So whenever we have an update which creates new variables, the acceptance rate ratio which guarantees the right probability distribution is the following. It's the expression for the new diagram over the expression for the old diagram. And this structure is very simple. Remember, all diagrams are essentially, they factorize into simple products. So basically it's a kind of ratio of a very few new propagators or old ones. And here comes this function which we use to seed the new variables. And whenever we remove this element in a complementary update, the structure is the same, but now this function, this arbitrary function, enters the numerator. And this function is up to us. It affects only the efficiency of the algorithm, but not the final answer. The final answer does depend on this function. Of course, just to have the algorithm most efficient, we want the whole thing, the acceptance ratio, to be close enough to unity. 0.5, say, would be very good, almost perfect. So that we really update the stuff rather than we reject each of the others. So that's basically the idea. The rest are some specific details, how we arrange the sampling process for a given configurational space of diagrams and stuff. But the theory just boils down to those two slides which I demonstrated.
Can I ask a
yes, sure.
question? I mean, If you have a theory with ultraviolet divergences, so that changing the topology changes the divergence structure of the diagram. How is that handled with your...
Then it's yet another complication. Then you have to introduce some regulator. So then everything comes at the expense of controllable systematics. First, you truncate your ultraviolet divergence. For example, if you would do continuous space fermions with some ordinary interaction, you would have to do that. Otherwise, the series will be asymptotic. And then you study your answer as a function of this truncating parameter. So as always, you first introduce some regularization, and then regularization in its turn introduces some systematics, and then you study your answer is the function of this systematics. Say your truncation momentum goes to infinity, your answer saturates it.
So gauge theories you wouldn't be able to handle?
Directly. Yes. Well, or only at the expense of controllable systematics. But
yeah, but there it's difficult. That's, there you cannot just use simple momentum theory.
Right. In any case with ultraviolet problem, first of all, you have to solve the problem. And also there are many problems with convergence of the series. So many series are just asymptotic. And that basically slide is all about convergence.
But you are basically thinking of lattice problems without gauge.
At the moment I'm thinking of either lattice or continuous space fermionic problems. But we have something for bosons as well and classical fields. So in the case of the main problem with this series is not even the fact that it's not positive definite, but the fact that it can be asymptotic. Putting aside this ultraviolet problem, which is the series, or each diagram can be perfectly defined, but the whole series can be asymptotic. It's a very serious problem. This slide is all about this problem, but it's basically Dyson's collapse argument, but you can circumvent this problem. For fermions, easily, if it's just a standard lattice theory, then there is no Dyson's argument at all, because of the discreteness. Fermions in lattice do not collapse. In a free space, for fermions, you can introduce a momentum cutoff. At the moment, I'm not ready to discuss more sophisticated cases when each diagram can have a problem. Okay, so basically, why do we care about diagrams rather than just other Monte Carlo representations like word lines? As I already mentioned, in the case of diagrams, we can do the macroscopic limit analytically, and this is a big difference. Because what normally happens with Monte Carlo, by quantum Monte Carlo, people mean some mapping of a quantum system in d dimensions onto a classical counterpart in d+1 dimension. Say, typical situation would be word-line representation. And as we all know, for fermions, there will be so-called sign problems. Some sign problems. So you change something locally, you change the topology of the word lines, and the sign of the whole configuration changes. And then the complexity grows as follows. It's an exponential where the exponent is the ratio of two volumes. The volume of the simulation cell and the correlation volume. So the volume corresponding to the linear size on the order of correlation length. And this ratio of two volumes should be really large, because otherwise we cannot reach the macroscopic limit. Otherwise we simulate something essentially finite size. And when this volume is reasonably large, this ratio can be 100, it can be more, and then it's the exponential, and that's how the sign problem kills us if we simulate a kind of chunk of quantum matter rather than a mathematical answer. In the case of diagrams, we simulate a mathematical answer. In this sense, our problem is zero-dimensional. We sample some just objects, and normally going to the order of expansion like 10 or 8 is enough to see the answer. So once again, it's not in the mathematical sense, it's not a solution to the sign problem, because the complexity, speaking mathematically, grows factorially. So the complexity in the mathematical sense can grow even sharper than this exponential growth. But the point is that to get a reasonable answer, say with % accuracy, we don't care. If we care or just the answer with reasonable and controllable accuracy, these can be good enough. That's
How do you
basically the
estimate
method.
accuracy? How do you estimate accuracy?
By truncating the series one by one and seeing how everything saturates. I will show you a picture of how we control the accuracy. So let's just discuss the Hubbard model, kind of hydrogen atom of strongly correlated physics. So this is the hopping term. So we have fermions with spin 1/2. So two sorts of fermions which live on a square, say square lattice. Actually, the structure of lattice doesn't really matter. So we have a hopping term, we have an on-site interaction. Once again, it's not really important that the interaction is on-site with diagrammatics. And we have the following diagram elements. This guy represents the interaction, and two propagators represent the two sort of particles. So basically that's the answer to your question, how we control the convergence. We truncate the series up to a given order. So this n star is the truncation parameter. It's the inverse. 1 over n star is the inverse truncation order. And we see whether our answer saturates or not. So here we have two-dimensional Hubbard model with the interaction. We measure interaction in the units of hopping. So the interaction in the units of hopping is 4. And the temperature, which is also measured in units of hopping, and the chemical potential are as follows. So this is the temperature which is significantly lower than the Fermi energy. So what we see, and the two quantities of interest are just the equations of state. So the energy per unit site, the energy per site as a function of temperature and chemical potential, and the filling factor. Question? Okay. And the filling factor as a function of temperature and chemical potential. So we go to higher and higher diagrammatic orders and we see this plateau. Then we say, okay, we have saturated to a given answer. Sometimes, so here a kind of convergence is by naked eye. Sometimes we use resummation techniques to enhance the convergence. And then we make sure that different resummation techniques lead to one and the same answer. So that's how we control the convergence.
How much computer time do you need for those data points?
Okay, it's also a good question. Just quite a lot. And normally just the bottleneck is the very last point. So you see, normally it works as follows. So just you have a decent, say, time, just you spend, say, 1 week for doing everything, and no matter what you are doing, because remember, the complexity is factorial. So normally what truncates us is the order of expansion. So normally we can always afford doing simulations during, say, 1 week on a cluster, having many. And that's basically, then the bottleneck is the maximal order which we can afford, because normally if you can afford doing 1 week of simulation on a cluster, you would prefer to use all this resource. But normally it's all about the error bar, about the demonstration that we have saturated to a plateau. Okay.
So does it saturate to a value that if you try this sort of more brute force method, it's the same value?
I will show you on the next slide. Okay, so that's basically the comparison with other techniques. So there is yet another controllable technique which is called high temperature series expansion. It works perfectly, but only at high enough temperatures. So these high temperature series becomes divergent at temperature comparable to the Fermi energy. But when it converges perfectly, and that's the comparison. We just reproduce this answer within the error bar. Also, so that's basically how we can control ourselves in terms of the Hubbard model at high enough temperature. If we go to lower temperatures, there is a nice method which is called dynamic mean field theory. It's an approximate method if we are talking of single-site dynamic mean field theory, but it's known to be pretty accurate. And what you see on this slide is kind of validation of this dynamic mean field theory in 2D with diagrammatic Monte Carlo. So just perfectly agree with this method. It's better to say DMFT perfectly agrees with diagrammatic Monte Carlo, because diagrammatic Monte Carlo is a controllable method. Now there is a kind of advanced version of dynamic mean field for a two-dimensional system where people do clusters. So it's a generalization of single-site dynamic mean field to cluster. There are many different versions of this generalization. This one is called DCA, and what we see is the following. It's basically when people with DCA go from 4 sites to 32, we clearly see that the curves saturate to our answer once again. And see, we are talking of really percent deviations because, as I said, the method, even the single site dynamic mean field is very accurate. Okay, so there is no question that basically everything is controllable if we use this. Of course, if we can afford going to higher orders when we see this saturation. So what do we have at the moment? So we have 2 ongoing projects for Hubbard model. One is ladder boldification of the lines, and another is Cooper instability. What I didn't tell you is the following, that with diagrammatic Monte Carlo you can actually do what is known as skeleton diagrams, which correspond to the expansion in terms of genuine Green's function. So basically you look for the Green's function, expanding it in terms of itself. So mathematically you get some severely nonlinear integral equation. But with diagrammatic Monte Carlo sampling, this expansion is almost as easy as sampling the bare series. This type of Monte Carlo is called, we call it bold diagrammatic Monte Carlo, just because everything is expressed in terms of the bold lines. So these skeleton diagrams, there is a kind of convention to represent them with bold lines. And we have already completed the boldification of interaction. Because remember, I was showing you only small enough interaction, like u over t equals 4. Because if we go to higher values of interaction, we have to go to higher and higher orders of expansion, and we cannot afford it with this type of approach. But if we do the ladder summation, everything is expressed in terms of effective, bold objects, and we have already completed the code. We collaborate with Eugene Deng from USTC, China, who visits us. And the code is written and it's being debugged. And yet another direction is Cooper instability, or more generally, all possible two-body response functions, including the Cooper channel. We do it with the group of Matthias Troyer at ETH. So we really want to see the pairing, the Cooper pairing, super conductivity in this system. And yet another idea which came to us pretty recently is that in fact we can incorporate dynamic mean field into bold diagrammatic Monte Carlo in a controllable way. So single-side dynamic mean field is essentially approximate. So, and the bad news about methods like that, they can be extremely accurate, but you learn about that a posteriori by comparing them, say, to controllable methods like diagrammatic Monte Carlo or just other methods. What we can actually do, we can incorporate this idea of dynamic mean field into diagrammatic Monte Carlo in an absolutely controllable way when there is no systematics whatsoever. So basically, part of the summation, you can view this as using the MFT as resummation. So the most crucial part of the series responsible for the answer is being done by DMFT type of methods. And the rest is done by diagrammatic Monte Carlo. For example, DMFT captures 99% of the answer, but you don't know it a priori. You use diagrammatic Monte Carlo just to sample the error bar. Let me just briefly describe you how it works. It's conceptually it's pretty simple. So you have the following expression for the Green's function in terms of the bare Green's function and self-energy. So the idea of dynamic mean field theory mathematically, it's very simple. It says, okay, actually for whatever reason, on a lattice, the self-energy consists of 2 parts, so-called local part and the rest. And the local part is the function of the local Green's function. So it's just the function which lives on a single side. So this integral over all momenta in the Brillouin zone means that we are talking of the function which is responsible for the single side only. So far there is no approximation. We just separated the self-energy into two pieces. What leads to an approximation is actually the idea that, and this is the essence of single-side dynamic field, that you can neglect this guy. And our approach is opposite. We are not going to neglect this guy. We just want to keep everything here and just use two different methods. So that's actually the flow of the information in the simulational process. So suppose at some point we have a good approximation to the Green's function, and then we do the following. We evaluate this local Green's function, and we have a solver, a dynamic mean field solver, which expresses the self-energy in terms of this Green's function. Normally we go the opposite direction, but when just in this approach it's other way around. So from the Green's function we extract self-energy, which just is a kind of tricky, but possible. And then simultaneously, so those two processes, solving for the local contribution to self-energy and sampling the rest, can go simultaneously. And you can show that actually there is no double counting and there are no approximations whatsoever. So then the two are combined into the self-energy, and then updated value or updated Green's function is evaluated, and everything just keeps running in this circle and ultimately converging to the Green's function. That's the idea. Now let me switch to the resonant fermions. Yes, question?
In these formulas, when you calculate P, it's an external variable, what you call Y at the beginning, correct?
Excuse me?
P.
Yes, momentum.
It's an external variable,
yes, yes.
like what you call Y at the beginning.
Yes. And there is also time and frequency. I just suppressed frequencies just.
So that means you actually have to sample a huge space, the time momentum space, in order to construct this beam function.
Yes.
You might try simply to construct for sigma prime of P the quadratic approximation, which is probably more than reasonable.
We can discuss it. We can discuss.
That would be much easier.
We can discuss it because it's a big question of how to optimize the data structure. So you touched a very important issue, how to optimize the data structure. But let us do it later because it will take long. You're absolutely right that just optimized data structure is crucially important for the efficiency. But let me just skip it. It's a technical question, very important but technical. Okay, so let me just switch to the resonant fermions. It's a kind of very hot topic. So the resonant fermions is the following system, which nowadays can be realized with cold atoms. So by means of Feshbach resonance, the interaction, which originally is very weak, the distance between particles is much larger than the size of the interaction potential. But what can be done, this interaction can be tuned to the resonance, in which case the scattering length becomes on the order of the interparticle distance. And the whole problem can be formulated as a kind of problem without the interaction, but with a very specific boundary condition like that, in terms of the many-body wave function in the coordinate representation. So we have two sorts of particles, spin up and spin down fermions, and the boundary condition, which is equivalent to this resonant interaction, is the following. Whenever two particles of different spins come close to each other, the wave function is supposed to look as follows. And the only one constant which controls the physics is the ratio of these two parameters, this constant B and this constant A. The ratio is constant C, and this constant actually, the dimensionality of this constant is the inverse length, and the inverse of this constant gives the scale to the scattering length if we would discuss a two-body problem. But it's a many-body problem, and we have two characteristic limits when the problem becomes weakly interacting. So if this constant C is much larger than the Fermi momentum, we have a weakly interacting Bardeen-Cooper-Schrieffer regime. We have Bardeen-Cooper-Schrieffer pairing on top of the well-defined Fermi surface. When this guy is large, this parameter C is large but negative, large in terms of the absolute value, we have a regime of compact bosonic molecules, so-called BEC, Bose-Einstein condensation regime. And what we have in between is so-called BEC to BCS or BCS to BEC crossover. And the most interesting situation, a kind of very convenient for theoretical study, is so-called unitary regime, when this constant is essentially zero as compared to the Fermi momentum. In this case, we have just some additional scaling symmetries, which are not that important for Monte Carlo, but just a kind of matter of extra convenience. So first of all, I would like to start with a kind of toy problem, but very popular nowadays. This is the problem of so-called resonant Fermi polaron, when we have just one extra particle. So we have a Fermi C, say with spin up particles, and we have only one spin down particle. And the question is a very interesting question. That's why this problem is kind of popular nowadays. Is what is this state? Of course, if we put a particle in a medium which strongly interacts with this particle, the particle gets dressed. It changes its effective mass. But something more interesting can happen. So if this particle just gets dressed, we call it polaron. It changed its properties, but kinematic properties, but it does not change its statistics yet. But if the interaction is strong enough, this particle, this fermionic particle, or a bosonic particle, if it's a bosonic particle, can form a bound state with one of the particles from the Fermi C, and it will change its statistic. Fermionic particle will become bosonic. Bosonic particle will become fermionic. In this case, we call it a molecule. Yes?
But you don't care, since you have only one particle, statistic doesn't matter.
Right, but the next step why people are interested in all this stuff, of course, up to one particle, they have a kind of dilute gas of them and stuff. Of course, I do not care. I just care only about two channels, a polaron and molecule. So in this particular problem. But just explaining why people are so curious nowadays about this problem is just the possibility of having a dilute gas of these particles. Okay, so basically diagrammatically we have the following polaron type diagram, and we have two channels, a polaron channel and a molecular channel. And what's interesting is that we do not have a potential here, because we can do... Yes?
Sorry, I don't understand the difference between
Yes.
the two diagrams.
That's what I'm going to explain. So you see this gamma. This gamma represents the interaction. It's a ladder diagram. But because in this problem, the size of the potential goes to zero, the ladder diagram becomes a line. It's like a line, this gap. So the difference, which is barely seen, is that here we start with this gamma. So it's a two-body channel. So this is a two-body channel. A molecule is seen as a pole in a two-body channel. And the polaron is seen as a pole in a single particle channel. That's the difference. Here we start with the green line, here we start with the brown one. Okay? But otherwise it's very symmetric. It's just the beauty of these zero-range interactions. And basically those are the answers. We have the answer for the energy of molecule and polaron. We have the answer for the effective masses. And we have this critical point. This is the point of avoided crossing. So because those guys carry different quantum numbers, they cannot hybridize. They just cross each other without noticing each other. And the lowest curve just corresponds to the state which is the genuine ground state. Here, if we go far away, the upper state can decay incoherently into the lower one. But the decay width, because of this phase space argument, is tiny, so that actually numerically we see both. We cannot distinguish, say, a genuine pole from a kind of very narrow peak. We see both as very good poles. because of this phase-space argument and very small difference between the energies. Okay, now it's basically a kind of experimental observation of the fermopolaron done in Martin Zwernein's group. So just within the arrow bars we coincide, which is not surprising. It's essentially an exact technique. And now I really want to go to a macroscopic system, because my main message is about macroscopic system of fermions. So resonant fermions at unitarity, and our observable, our goal is the equation of state. Say the number density as a function of chemical potential and temperature. So let me show just this technical slide, which is very important for understanding the difference between the bold diagrammatic Monte Carlo, which we were developing very recently, and the bare one. So here we have just two different temperatures. This is the inverse diagrammatic order, so we study the convergence. And we have the following. We have the bare expansion, those squares. And here temperature is high enough so that we can see a kind of convergence by a naked eye. But if we do error summation, this green curve, everything gets much nicer. We do not have those oscillations. We just have a kind of smooth curve which converges here. And our observable is the number density in some relevant units. So if we go from the bare expansion to the bold one, if we write everything in terms of the genuine bold propagators, the convergence gets worse. And this is an important message. So whenever you go to the bold diagrams, especially if you truncate your series just to the first diagram or to the first few diagrams, it's not guaranteed that boldifying the lines you improve the theory. Not at all. The theory can get worse, like here. You can ask the question, why then it's important at all to go to this bold series? The importance is that when you go to lower temperature, the behavior of the bold series is much, much better than the behavior of the bare series. With the bare series, we cannot go to low enough temperatures. Our basically oscillations explode, essentially explode. While the oscillations of the bold series remain more or less the same, and the relative amplitude of those oscillations is not very large. It's about 15%. Meaning that we can nicely resum the bold series. So those are the results of resummation of the bold series, which are perfectly consistent with the resummed bare series. And with these bold series, we can go to much lower temperatures. And the very last slide, which I want to show you, is the result. I'm not sure whether I'm allowed to release those results. Those are farm fresh results from Martin Zwernein's group. So this is the experimental data, very accurate experimental data for the equation of state in some relative units with respect to the ideal gas as a function of the chemical potential over temperature. So with bare diagrammatic Monte Carlo, we were able to go only up to this point, up to which we do not have controllability any longer. We cannot afford going to large enough terms of the series so that we control our error bar. So we had to stop here. And with bold diagrammatic Monte Carlo, we are able to go much further. And actually, it's not the end of the story. It's just our recent data, because basically we finished finished decoding and debugging kind of 3 weeks ago. So it's kind of our preliminary data with bold diagrammatic Monte Carlo, which is very kind of optimistic for us, because somehow we can definitely go much further, and we hope that we will be able to go up to this point, which is the critical point. And probably we will be able to resolve even Cooper instability. Thank you.
questions?
What's on the vertical axis there?
Excuse me?
Vertical axis, I missed it.
It's number density over the number density of the ideal gas. So everything is, as you know, measured in the relative units with respect to the ideal gas because of the scaling symmetry. So it's all about dimensionless numbers.
What would be the indication of the Cooper instability?
The Cooper
Yeah,
instability,
what would you look
oh,
for?
just the response. Because remember I was describing this gamma pair channel. You just look into this channel and explicitly see the divergence of the response function. It's very simple.
The DMFT calculations on the Hubbard model sees a phase transition, not an insulator transition. Can you catch that with this method?
It's a good question. So far we had difficulties because remember I was showing the result of the bare expansion. With bare expansion it's very difficult because it looks like this is a physics which requires large enough use. And at the moment we have finished the code which does the ladder summation. So far I would say no with bare expansion. But with the new code I don't know because hopefully because the whole business of ball-defined the interaction was basically the ability of going to large enough use when we can see essentially non-perturbative physics.
See, I want to go back on slide or two where you had, yeah, there. The one on the left. So you have on the horizontal axis one of the diagrammatic order. So that's point 2 being fifth order, correct?
Yep.
Yeah. But this is positive scattering length, if I see it correctly, right?
Yes.
So since the temperature is relatively high, basically you're in the regime where you expect the virial expansion to work more or less, maybe up to fourth, fifth order or so.
But even with the bare code, we can go further than the virial expansion.
No, I understand that. You see, my question is the following. If one computes the second virial coefficients for positive scattering length, you have a bound state that dominates the value of the virial coefficient, the fact that you have a bound state there. And what I'm surprised to see there, the fact that you can reproduce a bound state doing a perturbation expansion up to fifth order. You understand my problem? So you see, the bound state is a non-perturbative effect. You cannot obtain that correctly. So if you obtain the second virial coefficient correctly, you should describe the bound state correctly, and therefore you see this doesn't quite add up.
Somehow, I'm not sure I can buy the argument because.
Why not? You see, the virial coefficient is given by the scattering length, which is defined by the binding energy.
Right.
Period.
Yes,
Especially for
but
small
there can be a sort of logical gap. So
no, there is no logical gap.
no. I'm not saying that it's not given by the bindings, but
The zero range is scattering length alone. That is it.
You see, let me put it this way, because then I don't care about the temperature at all, right? Because suppose our temperature is 1 million times.
You measure the temperature, the binding energy.
Let me just right. But this virial coefficient remains the same if my temperature is larger than the Fermi energy by 1 million times. It works even better, right? So you see.
Fermi energy, I don't think it matters at high temperatures.
Look, my point is that there is a finite range of convergence of this method because there is no Dyson collapse. So, because your argument would say that actually this approach cannot catch anything going beyond this virial.
Let me ask you a different way. Calculate the bound state. Two particles. You do diagrammatic expansion. Calculate the bound state. I don't think you do in a perturbative expansion, period. If you calculate the propagator, you can calculate the bound state. Calculate the propagator for two particles.
You see in the slide, okay, let me show you something, okay? Because before that we were discussing diagrammatics. For Fermi Polaron, and for the molecule. And this guy, this molecule, is exactly the bound state. We were able to see the bound state.
I don't think you're going to prove it.
To prove what?
No, they're going to get a bound state. You see, diagrammatically, you cannot get a bound state, period.
That's
There's
very
no
strange.
opportunity.
That's very strange because the pole, that's what the pole in this channel is a bound state. The pole in this channel is a bound state.
I'm not sure you did. You probably get something which looks like, but I'm not sure you get it.
You see, if it looks like an elephant
No,
in all possible ways, then it is an elephant. Okay, let me also give you yet another thing. So the people, people are most excited nowadays about so-called Shvi ansatz. It's an approximation, but for whatever reason, it works very well. And there are Shvi. There is a Shvi ansatz for the bound state. So people explicitly construct the bound state. It's approximate, but it's so good.
But
And
that's already in zero order you introduce the bound state. You don't have, you start from free or plane waves.
Yes, we start from plane waves, but Shvi starts with explicitly writing the bound state, the variational wave function for the bound
But
state.
that I expect to converge, but not this one.
But the agreement is absolutely perfect, including the effective mass. Not only the energy, normally with Polaron type problem, energy is much better with variational function, but even the effective mass comes absolutely perfect when they write this variational ansatz or explicitly bound state by hand. So in the first place, I'm not ready to agree that we miss a bound state.
Well,
Maybe it's a good idea to sort of continue this discussion over coffee if there's no other quick questions. Let's thank the speaker again.
Coffee is here.
We convene in 15 minutes or so?
Coffee break, yeah.
15?
5-10 minutes.
10-15 minutes, yeah. Oh, sure.